this morning to read? Well, I guess we should make a start, perhaps. Perhaps. Okay. I'll introduce today's speaker. Is Michael Lyson, who's come from the ICHEC, the Irish Centre for High Computing. He's going to tell us today about optimizing code for the new Intel Xeon Phi architectures.
Hey, thanks very much. So I see I might be competing against the drill, so hopefully you can hear me this morning. So my name is Michael Lyson. I'm from ICHEC. A little bit on ICHEC before we start. So the Irish Centre for High Computing is the national HPC centre in Ireland. So there are equivalents in most European countries. And I lead the Intel Parallel Computing Centre there. So there are around, I'd say, 30 Intel Parallel Computing Centres worldwide. They were recently set up by Intel to focus efforts on modernizing software for Intel Xeon Phi. So some of the other big HPC centers around Europe are also members of this Intel Parallel Computing Center program. So I'm going to be talking about Intel Xeon Phi, obviously, for most of the day today. A little bit of background on these notes. The course is inspired by a mixture of ICHEC, Intel, and Intel third-party training party partner material, particularly material developed by Colfax International, which is a third-party training provider for Intel. And the hands-on exercises that we're going to do later on this afternoon have been developed by ICHEC. So in terms of an outline for the course, here's what we're going to try and cover today. There's quite a bit. We're going to give you an introduction that will set the tone for the course, give some context for why there's a growing interest in Intel Xeon Phi as an architecture. And then we're going to do a bit of a deep dive on the Intel Xeon Phi architecture. So can I ask, has anyone worked on Xeon Phi before, run code or developed on Xeon Phi? Show of hands, so I see one over there. Okay, so there are now officially two generations of Intel Xeon Phi. First is codenamed Knight's Corner, and then the second generation is codenamed Knight's Landing, and that's only being released on the market as of Monday last week. So it's very new. Then we're going to talk about general approaches to programming the coprocessors. So there are various models one can go about to program the coprocessor, and I should be quite clear on that. When I mention the word coprocessor, I'm talking about Knight's Corner typically, whereas when I talk about processor, I'm typically talking about Knight's Landing or Xeon. Okay, so Knight's Landing also comes in the flavor of a coprocessor, but it's anticipated that flavor won't be as popular as the coprocessor flavor for Knight's Corner. Then we're going to talk about performance fundamentals. We're going to talk about vectorization, which is key to getting performance on the Intel Xeon Phi platform. We're going to talk about multi-threading. So in the same sense that you need to multi-thread your software for multi-core platforms, you need to do it for Intel Xeon Phi, only there's that bit more onus on you to get scalability in terms of threading on the Intel Xeon Phi, because there are 61 cores on the Knight's Corner coprocessor. And we're going to talk about memory optimization. So this is where things get particularly difficult on Intel Xeon Phi, and where performance engineering is really, really crucial around the areas of memory optimization. And then we're going to talk about approaches to using MPI on the Intel Xeon Phi platform as well. So we're going to talk about it in terms of using it natively on the coprocessor, and then across coprocessors, and then across coprocessors plus processors, so in a heterogeneous environment as well. So hopefully that outline is clear to you. So in terms of an introduction, so I said we'd set the tone. So here's a schematic on CPU growth trends over the last few years. So what we're looking at here is essentially the core increase, so the increase in core counts on the bottom of the top 500, so from 496 to 500. So rather than choose the top 10 or the top 5 supercomputers in the world, which can be quite particular in some sense. I mean, they're, certainly they have non-commodity features about them sometimes. I've gone for the lower part of the top 500 list, and you can see that there's been a really, really dramatic increase in core count since 1993 or thereabouts. So you're going from 10 cores in 93 up to about over 10,000 cores in the bottom 4 of the top 500 list as of today. And then you can see Spec Int is a famous benchmark, and you can see that there's been a commensurate increase in speed in that benchmark with the increase in core count that you've seen in these bottom top 500 computers. And I guess my understanding is that you've done a little bit of background on HPC over the last few days. You've probably heard about the reason for this dramatic increase in core count. The main reason is down to this so-called power wall, which has slowed frequency increase on cores over the last 2 decades. So it means that core frequency has saturated, and because core frequency has saturated, we need to introduce more hardware parallelism to our platforms, because we're not going to get performance gains from the increase in core frequency anymore. We're only going to get from gains in parallelism, hardware parallelism. So what that means effectively is that you're going to continue to see dramatic increases in core count, and you're also going to see increases in vector lengths, so the length of vector units on multi-core, many-core platforms as well, which reflects an increase in data parallelism. So core counts are on an exponential growth trend, and they're much faster than single core performance due to the sheer amount of cores on these emerging many-core platforms. So here's another graphic showing an exponential growth in data parallelism. So I'm sure you've touched on various different vector instruction sets that you can see on x86 platforms over the last decade or so. So what came about in the early 2000s, late 90s was the SoC instruction set, and now we're in the AVX era. And as of Monday, we now have AVX 512 available to us. So what that trend in instruction set shows on the horizontal axis is effectively an increase in the width of vector units. So AVX and AVX2 are 256-bit vector units. AVX 512, as the name suggests, is a vector unit of 512 bits. So that coupling with the increase in core count means that we've seen a 500x fold increase in data parallelism since the mid to late 90s. So we're seeing this massive flop per chip increase due to the increase in vector units and due to the increase in core counts over the last 2 decades. And as a result, we've seen a relative flop increase. You can see it there of in and around 600 flops on these many core platforms. So parallelism is the way forward. There's no doubt about that. You've heard the term, no doubt, the free lunch is over. The term means that parallelism is now, there's no doubt about it being exposed to the software developer to the extent that the software developer needs to take hardware parallelism into account for the first time. It's been hidden away for quite some time from the software developer, but now the developer is genuinely confronted with the challenges of hardware parallelism, namely in the form of increasing core counts and wide vector units. So we're now dealing in a world of lots of threads and lots of data parallelism. So the onus is on the software developer to expose that parallelism in their software algorithms. So can I ask you at this point what domain you guys are working in? So Just shout it out. Is it the one domain, or are you all working in different domains?
Yes.
Okay, so can I get a cross section of those? Anyone working in material science? Anyone care to shout out a domain?
Numerical linear algebra.
Okay.
Complex and turbulent flows.
Okay. QCD.
Computational biophysics.
Okay. Okay, so a wide range of domains. Okay, so systems are becoming highly parallel, more vectors, more cores per CPU, and more CPUs per system. And single thread performance is increasing at a slower pace. So if you look at the Intel Xeon Phi architecture, and we will be looking at it in closer detail, you'll see that the frequency per core is much lower than you would see on a Xeon system. Xeon systems, their core frequencies are in and around 2.5 gigahertz per second to 3 gigahertz per second, whereas the frequency of a core on the Intel Xeon Phi is more like 1 gigahertz per second. Okay, so what that means in effect is, and that's what the sentence speaks to, is that the per core performance on many core systems is actually falling off rather than increasing, and the reason for that is due to that dramatic drop in core frequency. So significant performance potential for applications that parallelize and vectorize. So that's key to our understanding for today's session, that you won't be able to get performance on the Intel Xeon Phi platform if you don't parallelize your software. If your software is sequential, you're not going to gain from the Intel Xeon Phi. There's no point in buying it, there's no point in running on it. It's a hugely, massively parallel system, and it will only work for massively parallel software. Okay? So if at any point if you have questions, don't hesitate to fire them up. Okay? If I'm using terminology that you're not familiar with, again, stop me, and I can explain that. There's no problem. So there are plenty of solutions in play when it comes to hardware, and when it comes to software, and when it comes to parallel programming models. Okay? No doubt you've become familiar with them over the last week or so, or even prior to the course here. So in terms of hardware options, we have our CPUs. So in HPC, we're typically talking about Xeon platforms, typically E5 Xeon platforms. So they're the type of Xeon processors you'll see on Fionn, which is the national supercomputer here in Ireland, and which we'll be logging into later on this afternoon. So these are multi-core CPUs typically nowadays. The latest multi-core CPU targeting the HPC market is Broadwell. Okay, so some of you might have heard about Haswell. And then the next one coming down the line is Skylake, in Intel's typical tick-tock release of processors. CPUs have been around for a long time. They won't be going anywhere for quite some time. They're general purpose in the sense that you can pretty much run any software on them. And most of the server market out there is made up of x86 Xeon processors. So then you have GPUs, particularly general purpose GPUs. So you've probably heard about these. Have you been programming on GPUs, any of you?
Well, during the previous workshop, I had some lectures in GPU programming.
Okay, here in Dublin, or?
No.
Okay. Okay, so you're somewhat familiar with GPUs. The big company that pushes GPUs onto the HPC market is NVIDIA. So NVIDIA are traditionally a gaming company, and then I guess in the early 2000s, late 90s, the scientific computing community realized that there was some commonality in interests between what the scientific computing community was interested in terms of floating point hardware, and what the gaming industry was interested in terms of floating point hardware. So the gaming industry has a kind of an insatiable demand for floating point hardware, the same way the HPC industry does. So scientific computing software developers looked at these GPUs and saw that, okay, I have all of these floating point units on the GPU. Can I leverage these in some way? It's a massively parallel platform, and they did so with quite some success. And what emerged as a result of that success was the CUDA programming framework, which is still today the most popular means of programming a GPU. So a point to note on CUDA is that it's a proprietary programming model in the sense that it's owned by NVIDIA. Okay, so it's not open source. It's not an open standard. Okay, and that's quite restrictive in some ways, and some people in the community have been turned off by that fact because nobody knows for sure whether CUDA will be around forever. Okay, nobody knows for sure whether OpenMP will be around forever, but because OpenMP is an open standard backed by a very large and wide community, the risk is possibly somewhat lower. That's not to say that CUDA is not a good programming model. It's a great programming model when it comes to targeting NVIDIA GPUs. But the problem with CUDA is you can't target any other GPU with it. Okay, so there is an open standard for programming GPUs. It's known as OpenCL. Okay, you can program pretty much anything with OpenCL. That has its advantages and disadvantages. The issue with OpenCL when it comes to HPC is that it's not strongly backed by either Intel or NVIDIA. NVIDIA, for the reason that they want to keep pushing CUDA as much as possible, and Intel because they just haven't had as much success with OpenCL in terms of performance as they have had with OpenMP. So it's something to bear in mind when choosing a programming model. That being said, there is also an open standard directives-based model for programming GPUs that's emerged on the market quite recently. It's known as OpenACC. Okay, so it shares some commonality with OpenMP, and there has been talk for quite some while of those two standards merging at some point, but it hasn't happened. Okay, so there are some fundamental differences between OpenACC and OpenMP. We can touch on those later on if you're interested. But at least there is a high-level means of programming the GPU that is emerging. So then there are FPGAs. So has anyone heard of FPGAs before? Okay, so field programmable gate arrays are kind of known as the chameleon of many core platforms because you can configure the hardware to suit your needs, which is quite unique. Okay, so they are programmable after the fact, basically, so that rather than tune your algorithm to a given fixed hardware platform, you can, in effect, tune the hardware for your fixed software algorithm. Okay, so that's quite an unusual angle to things. That being said, there are limitations when it comes to tuning the hardware, as you can imagine. There are restrictions and constraints on that, and more often than not, you need to significantly engineer your software to map to the FPGA. So it's a particularly difficult hardware platform to target. There have been recent initiatives to support high-level programming models for programming FPGAs. It's yet to be seen whether these are truly successful or not. Okay, so you can actually program an FPGA with OpenCL now, and in effect, OpenCL is not that different to CUDA. In some ways, it's not even that different to OpenMP. It's a high-level programming model, effectively. So it's quite amazing to think that you can program an FPGA with a high-level abstraction nowadays. But as to whether you can get performance or the performance you would expect from the FPGA, I think there's still some way to go in finding out whether we can really achieve that or not. So one of the attractions about FPGAs is that they're low-power platforms, very, very low-power platforms. Okay, so they're very energy efficient. And a lot of the conversation that we're having today is in the context of exascale computing as well. And not even exascale computing, we can say deep petascale computing. So I'm sure you've touched on the roadmap to exascale computing over the last few days, the constraints on achieving an exascale platform by in and around 2022, which has been set by the DOE in the US, is that it has to come under the envelope of 20 megawatt power envelope. Okay, so that's the limiting constraint on an exascale machine. So, you know, when we talk about many core platforms, the reason for these many core platforms is due to the power wall fundamentally, but it's also due to the fact that we need to achieve a sustained exaflop by 2022 under the envelope of 20 megawatts. So there are lots of people turning to FPGAs as part of research investigations as to whether FPGAs are a viable component on future exascale systems. And then you have more exotic applications, specific accelerators. So again, these would typically come in the flavor of an FPGA, but there are some slightly more exotic architectures out there as well. I don't think we'll focus on those in the extreme way today, though. So then when it comes to programming models, there are obviously different flavors as well. So we have MPI. So a show of hands as to who's familiar with MPI. Okay, so nearly all of you are programming with MPI. Okay? So again, a very well-known open standard for typically distributed memory parallelism, but not limited to distributed memory parallelism. You can use MPI on shared memory systems as well, and sometimes quite effectively. So we're now at MPI 3, actually 3.1. So there are a lot of features in MPI 3 that people typically underexploit, but shouldn't anymore, because a lot of those MPI 3 features are actually targeting many core platforms. Okay, so it's worth bearing in mind. So if you're the type of MPI developer that typically employs MPI 1, think about that, and think about looking at some of the new features of the standard, which are typically underutilized, because some of those features are very well suited to many core platforms. And I can talk about those later on if we have time. Then there's OpenMP. So OpenMP has been around for some time. I take it all of you are OpenMP programmers to some extent, or have some familiarity with that standard. So we're now at version 4.1 of the standard. Okay, so have you employed any OpenMP 4 features over the course of this training course or prior to that? Okay, so you're familiar with the offload concept in OpenMP?
Yes.
Okay, and any vectorization features?
Some, yes, there was some.
Okay, okay, so that's great to know, because they're key features for Intel Xeon Phi. So maybe you were doing that in the context of the Intel Xeon Phi.
We never had the expert example the OpenMP4, but we usually course on OpenMP.
General OpenMP.
Mine is less.
Okay, so we can certainly mention some of those features today. So the two key ones when it comes to Intel Xeon Phi, and this is quite interesting in terms of recent developments, are the offload features in OpenMP. Okay, so and I'll touch on those more deeply, but not to any great extent. And the reason why is because I want to talk more about Knight's Landing today, rather than the coprocessor. Okay, so I want people to think about Intel Xeon Phi more in terms of a processor rather than a coprocessor, because that's the trend. Okay, so you will see people start to think about Intel Xeon Phi more as a processor that isn't fundamentally that different to Xeon in some ways.
So I'm not sure what the difference between a coprocessor and a processor.
So yeah, and don't worry about it, I'm going to go into a deep dive about that. But fundamentally, a coprocessor comes in the form factor of a PCIe card, just like a GPU typically does nowadays. And a processor is typically on socket or on the motherboard, so that you're not concerned with having to transfer data over the PCI Express bus, which is typically a bottleneck, and typically something that's quite intrusive to your software development process, because If you need to offload to a device, your software typically needs to reflect that offload to the device. So you actually have to explicitly program that offload into your software. And that's quite intrusive. And it's quite intrusive for software that targets GPUs and has been for the coprocessor to some extent as well. So although we're going to be doing our development on the coprocessor, and this is quite strange, we're taking this course at quite an interesting time, okay? Because the KNL Knights Landing has only just emerged on the market as of Monday, okay? And the most popular flavor of the KNL will be the on-socket flavor, i.e. the processor flavor. But everyone and everything has been shaped in terms of the coprocessor to date. Okay, so we're seeing this switch from coprocessor to processor only within the last 7 days. So I'm going to be mixing our discussion quite a bit between the two today. But when we think about Xeon Phi, don't think about it as an exotic device because it's a coprocessor, because it comes in the form factor of a PCIe card. Think about it in terms of a Xeon processor, just one with a hell of a lot of cores on it. And a slightly more complex memory model as well, okay? But fundamentally, it's just a very big Xeon processor with a lot of cores, with a lot of parallelism and a slightly deeper memory hierarchy, which is very, very important to contend with. But don't think about it as some sort of accelerator. That's basically what I'm getting at here. You've heard about this term accelerator. Xeon Phi is not an accelerator. It's a many-core processor. So then we have language extensions. CUDA is a language extension. It's a language extension to the C programming language. OpenCL is a language extension. It's a language extension to the C99 programming language. Okay, so they're programming frameworks that are effectively extensions to languages, existing languages. We have accelerator-specific APIs. So that might include OpenACC, for example. And then we have more exotic PGAS languages. So anyone familiar with PGAS languages? So PGAS, the idea of it is that it basically hides all that message passing that goes on in MPI from the programmer. It abstracts it away. So a really nice PGAS language is Core Fortran, so Fortran 2008. Sorry, go ahead. Yeah, OpenSHMEM or SHMEM, yeah, exactly. So, yeah, so that's an interesting one. So in some ways, it's quite similar to what a PGAS language is as well. It certainly influenced PGAS languages for quite some time, and it reflects what a PGAS language is fundamentally. So yeah, you're dead right. It's very, very similar in some ways. So Core Fortran, any Fortran developers? So there's nothing to be ashamed of. I'm a big fan of Fortran as well. I think everybody in HPC should program Fortran. It makes life a hell of a lot easier. Core Fortran, are you familiar with that concept? No. Okay, so it's actually in the standard. It's in the Fortran standard now. So it's available. If a Fortran compiler supports Fortran 2008, it supports Core Fortrans. So the idea is that rather than typically say if you're dealing with stencil-based code, or you're dealing with, say you want to distribute a very large matrix, and you have to do those message passing calls explicitly. Well, what Core Fortran will do is it'll build an array for you, a very large matrix effectively, and distribute it for you behind the scenes, and do all the message passing behind the scenes as well. You lose flexibility, there's no doubt about it. But what you do lose in flexibility is an increase in maintainability of your software, and also often an increase in performance, because you leave it to the underlying runtime system to decide how best to do those communications behind the scene. It's a balance. I'm not guaranteeing that that's going to be the case, but I think it's definitely worthwhile checking out if you are a Fortran developer. So software story is important. That's obviously the case. So we're talking about hardware a lot today, but we need to talk about software. Obviously, we are all software developers. So it's important to change software for parallelism in a manner that preserves investment. So are any of you working on what I call community codes? So community codes are existing large-scale codes that the community works on together. Or are you typically working on your own software for your own research needs? So you're developing your software from scratch, and it typically remains in-house in a research group and doesn't go outside that research group. Community code. And is there a name to that community code? Is there a name for the community code that you're interested in?
Well, it's not really a name. I mean, it's sort of private code for the community. So that's just, I mean, it's basically a code for that is Boston. But,
Okay. But the community works on it in some ways, not just you, right?
Exactly. Other research.
Okay. Yeah. And yeah, perfect. Anyone else? Everyone else working on their own software effectively?
So I'm working on mine also. So
Okay.
I guess most people also do that.
Okay. Okay. So certainly when you're working on your own software, or certainly if you're working on community code, this is really important to think about. You might think that I'm kind of overemphasizing this point, but think about it in terms of the longevity of the software that you develop. If you want to turn your software into community code, you want to share it via GitHub, which I strongly encourage people to do. It's a great way of finding bugs, that's for sure. Then think about the programming models that you're going to be using. Do you want your software to just lie around for a year and everyone forget about it afterwards? Think about all the investment that goes into your software. Or do you want it to leverage open standards so that it exists beyond your lifetime in that particular domain? Or if you want to stay in your domain, become a leading researcher in your domain, you will most likely leverage the software that you're developing right now and build on top of it. And if you do that, do it with clear design principles when it comes to your software. And a lot of those should rest quite firmly on the type of programming models that you choose. So, maybe think about whether you choose an exotic programming model. And maybe exotic is the wrong word here, but maybe I should be saying a proprietary programming model like CUDA, and whether CUDA will be around forever, okay? Or whether I should choose an open standard model. These are all things that you should think about at an early stage of your performance engineering on your software. So software should continue to run and perform well on future hardware. That's another thing to bear in mind here as well. Okay? So one of the nice things about Xeon Phi and OpenMP and MPI is that there is this design principle that when I target Xeon Phi as of, let's say, a given iteration of Xeon Phi, i.e., let's say, Knight's Corner, as it exists on the market today, then my software, if it scales well on KNC, should also scale well on Xeon Phi Knight's Landing as well. Okay, so that's kind of built in to the Xeon Phi model. Okay, whereas if you're dealing with more exotic hardware like FPGAs and maybe even GPUs to a certain extent, there's no kind of real guarantee that the software that I develop with CUDA, which is often very much targeting a given version of an NVIDIA GPU, that it will run effectively on a future version as well. Okay, I'm not saying that won't be the case, but it's slightly trickier when it comes to GPUs and FPGAs. Okay. So, and you're maybe familiar with that idea from running on Xeons. If you run on a let's say a Westmere Xeon from a few years ago, and then you're running on Haswell Xeon, your software will have scaled. Probably will have scaled quite nicely. Okay, now that's not the case when you map from Xeon to Xeon Phi. We'll be talking about that in a while. Advisable to choose programming models that will last long. That's the point I'm trying to emphasize here. Okay? Software generally used for decades, much longer than hardware. That's for sure. And here's some examples. I know the resolution on this is quite poor, but if I look at community codes here, I see the UK Met Office Unified Model. Okay, so that's the code that they use for their operational forecasts in the UK. And that's been around since 1990. Then you've got NWChem, which is maybe closer to community code that some of you will be interested in, so it's material science software code. Again, early 90s. WRF is another weather forecasting code, community code. Late 90s. And then you've got some codes that go back to the 70s that are still around today, okay? So there's a massive, massive problem for hardware manufacturers, technology providers, because they have to confront the challenges of mapping these legacy codes, which are often very large in terms of numbers of lines of code. Okay, so these weather forecasting codes are typically millions of lines of code. They're really legacy codes, okay? And they need to start putting these legacy codes on massively parallel hardware platforms so that they can properly exploit them. So it's a huge undertaking. And it's a big problem. It's a big challenge for Intel. It's a big challenge for NVIDIA as well, because these codes have been designed from a sequential angle up until now. You might think that parallelism, hardware parallelism, has been around for a long time. It hasn't. It's been around since about 2006, really. Genuinely been around since around 2006. That's not that long ago. That's very, very recent when it comes to the software market. 99% of the world's software is sequential in nature. And hardware is only getting more parallel. So computing platforms. So these are the platforms that we're going to be touching off today. Okay. So we're obviously going to shape a lot of our discussion in terms of CPUs. Okay. Namely Xeon CPUs, because they're the platforms that are of interest to the HPC market. They're E5 Xeons are high-end CPUs that typically target the HPC market. They're the CPUs that are in the Fion system, which we'll hopefully be able to log into later on this afternoon. The latest Xeon on the market is Broadwell. Next one is Skylake. Then we're going to talk about Intel Xeon Phi coprocessor, codenamed Knight's Corner. These coprocessors, just as the processors, come in various different SKUs, okay? So different form factors to suit different needs. The one that we're going to be using on the Fion system is the 5000 series. So 5100P is the particular SKU of the coprocessor that we're going to be leveraging. So the differences in SKUs might be slight differences in core counts, for example, or a slightly different terminal design power, or one SKU might have more DRAM memory over another SKU. So for example, if you have workloads that demand quite a large memory capacity, you might choose the 7000 series, which has 16 gigabytes of DRAM, rather than the 5000 series, which only has 8 gigabytes of DRAM. These are all cost considerations, because if you want more memory, you have to pay more money. Okay? So then we're also going to be talking about Intel Xeon Phi processor. And here's what I really want to underline, this word that is misspelled by me. Processor, okay? So it's not coprocessor. It comes in the flavor of a coprocessor as well, but what's of most interest to software developers, and particularly in the HPC market, is the on-socket processor flavor of KNet, okay? Because it means you don't have to worry about all this horrible data transfers over the PCIe bus and so forth, which impacts performance and impacts software development as well. So this is on socket, and that's a socket that the guy has in his hands there. So it's quite amazing to think that you have an Intel Xeon Phi that can fit on a motherboard right now. So let's have a look at product performance. So many core coprocessors, Xeon Phi versus multi-core processors. Xeon, you get better performance per system and per watt for parallel applications. Same programming methods, same development tools. So this is something that I'm going to be emphasizing throughout today, that what's different about the Intel Xeon Phi versus GPGPUs, because both are many core, is that with Intel Xeon Phi, you can use the same programming models that you've typically used on x86-based platforms. You can use the same tools, all the same software development environments that you're used to already, you can use on Intel Xeon Phi. That's not the case for GPGPUs. I'm not trying to undersell GPGPUs today. They're magnificent platforms when it comes to getting performance. Massively parallel. If you can parallelize your software effectively, you will get performance gains on GPGPUs. But what I will say is that GPGPUs are typically more difficult to program in some sense. More difficult to definitely port your software applications to initially. Now, in terms of getting performance, the Intel Xeon Phi is probably just as difficult as programming a GPGPU. And that's something that a lot of people don't fully appreciate. That although you can use C, C++, MPI, OpenMP, you have to use them in fundamentally different ways because it is very difficult to extract performance on the Intel Xeon Phi, even though it promises a lot. So here's some comparisons, albeit marketing comparisons between Intel Xeon Phi coprocessor. You can see it's the 7000 series, series of the card versus the NVIDIA K40. I think the best NVIDIA GPU platform on the market is, again, things have changed because there was a very big supercomputing conference in Germany last week, ISC, where they released a lot of new hardware onto the market. Let's say it's still the K80, okay? They have the P100 on the market now, but that's typically targeting deep learning workloads rather than HPC workloads. So K40 in terms of performance is quite close to the K80. So you can see that these are Monte Carlo Black-Scholes simulations that are interested in the finance community. You see that Xeon Phi can deliver better performance than GPUs. Intel architecture, product performance, a little bit more on that. So this is maybe a workload that's of more interest to you. This is a linear algebra workload. I'm sure a lot of you call DGEM in your software applications, matrix multiply, double precision matrix multiply. This is with the MKL library. Hopefully you all leverage MKL if you're running on Xeons, Intel Xeons. So you can see you're getting over a teraflop of performance in double precision on Intel Xeon Phi. Okay. So that's hitting the roof of what the Intel Xeon Phi coprocessor can offer in terms of double precision performance. In terms of single precision performance, if that was an SGEM rather than DGEM, you get double that number. And it's doing all of that in a terminal design power of about 250 watts. So here's a bird's eye view of two platforms, Intel Xeon and Intel Xeon Phi coprocessor. You can program it C++, Fortran, OpenMP, MPI, we know that already. But look, Intel Xeon Phi, you can use the exact same programming models. That's great. You don't need to use CUDA. You don't need to use OpenCL. Standard Linux operating system, it has a special Linux distro on the coprocessor, okay? Lightweight distro, a lot of it is designed to take into account that it's a coprocessor rather than a processor, okay? Up to 768 gigabytes of DDR3 on the Xeon. 3 to 16 gigabytes, and that reflects those differences in SKUs that I mentioned earlier on. GDDR5 RAM, okay, it's slightly faster RAM. It's the type of RAM you'd see in GPU rather than an x86 processor. In and around 18 cores, so the Broadwell has 18 cores per socket. Typically, you can get different SKUs of that as well, but you can get up to 18 cores on Haswell at least per chip. And each of these are in around 2.5 to 3 gigahertz per second in terms of clock speed per core. You can frequency downscale and upscale these core frequencies as well. This is what we're learning more. And then here's the killer, up to 61 cores on the Intel Xeon Phi. Okay, so there's your massive hardware parallelism. Because of the massive hardware parallelism, you've got to downscale that frequency quite significantly per core. And you can see that comes in at around 1.2 gigahertz per core. So this is why if you run sequential code on the Intel Xeon Phi, you're going to suffer big time. Because the core is way, way weaker than the core on the Xeon. Okay? So you need to parallelize over all the cores and over all those vector units to get the performance on Intel Xeon Phi. 2 hyperthreads per core. Some of you may have benefited from hyperthreading in some of your workloads before. Maybe a lot of you haven't. I know I work on a lot of software that can't benefit from hyperthreading. Xeon Phi, you have to use the 4 hardware threads per core. Now, I'm not going to get into the particulars on the differences between hardware threads and hyperthreads, okay? But bear in mind that there are 4 threads per core. There are 4 hardware threads rather than software threads. Again, there's slight nuance there in the differences between the two that you don't have to be too worried about. But the point here is that you have to, in order to get optimal performance on the Xeon Phi, you have to use at least two hardware threads per core. because the cores on the Intel Xeon Phi are in order cores. They're not out of order cores. Okay? So what that means is that there's increased latency when it comes to remote fetches on the Intel Xeon Phi that you need to hide by way of using a second thread on the core. So what that means in effect, okay, is that you have to use 2 threads per core, which means you have to find and expose more parallelism in your software than just 60-way or 61-way parallelism. You need to double that and go for at least 120-way parallelism in your software when it comes to multi-threading only. I'm not even talking about the vector units right now. 256-bit AVX vectors on the Xeon. On Broadwell, that's actually AVX2. Okay. ID Bridge that we're going to be using today, it's still AVX, but they're both 256-bit wide vector units. And here's the second killer. So here's the first 61 cores. Here's the second. More hardware parallelism. 512-bit vectors on the coprocessor. Okay. So these are instruction. This is an instruction set, a vector instruction set, IMCI. Let's call it IMC for today. Nobody really gives it a name. It's just called the KNC vector instruction set. We can call it that as well, okay? Because it was never intended to be around for very long. It was just to fill in a gap between AVX2 and AVX 512. Because as of Monday, last Monday, with K&L on the market, we're now talking AVX 512. Okay, so when you program on the K&L, you'll be using the AVX 512 instruction set. But because we only have access to the coprocessor for this course, and because there are still a lot of coprocessors out there in the system, any Intel Xeon Phi system that you tap into over the course of the next few weeks at least will still probably be a KNC coprocessor. You'll be leveraging this instruction set, which is particular just in the Knight's corner. The interesting thing about AVX 512 is that it will be compatible with AVX, the AVX instruction set that you'll see on Skylake. Okay, so they'll be fully portable between the two. The first Xeon processor that will offer up AVX 512 will be Skylake. So the very first Intel product to offer up AVX 512 is Intel Xeon Phi, Knight's Xeon. So Intel Xeon CPU die organization. So this is the CPU we're talking about here, the Xeon. General purpose platform for demanding computing applications. I think we can all agree on that. Certainly general purpose, and it can be used for demanding computing applications. Still a big component in the biggest supercomputers in the world. There's no doubt about it. All the biggest supercomputers in the world still have Xeon as their principal chip component. Okay, so up to a teraflop per second in double precision, up to 2 teraflops in single precision, up to 768 gigabytes DDR3 RAM. And here's something that's maybe slightly more new to us. It offers 126 gigabytes per second DRAM bandwidth. So one of the things we're going to try and find out today is our software memory bandwidth bound or is it compute bound? So can I ask you guys right now if you have any feel for that in terms of the software that you're interested in developing? Is your software compute bound or memory bandwidth bound? Memory bandwidth bound rather than memory capacity bound, right?
I think so, because it's sparse.
It's sparse, so it is. Yeah, certainly it'll be memory bandwidth bound. Yeah. Anybody else? Anybody dealing with compute bound problems? Dense matrix multiply, yeah. Anybody else? Any memory bandwidth bound people? More than likely you're dealing with memory bandwidth bound problems nowadays, okay? If you're dealing with an application that uses a lot of linear algebra, particularly, not particularly, dense linear algebra, not sparse. Sparse linear algebra is typically memory bandwidth bound. It's actually typically memory latency bound, more so than memory bandwidth bound. But if you're dealing with dense linear algebra, if you're using LAPACK and BLAS routines that operate on dense matrices, you're typically dealing with compute bound problems. And that's great. because it means you don't really have to worry about mapping your software to parallel architectures, because it's been done for you already by Intel, because you just leverage the MKL library. Nobody can do it better than Intel when it comes to dense linear algebra. The MKL is state of the art. Don't try and beat it unless you want to have a research career in linear algebra on many core platforms. Okay? Make sure that you don't use your own matrix multiply routines. Use MKL. Okay? So if you're memory bandwidth bound in terms of the algorithms that you're interested in, memory bandwidth is the key feature that you're interested in a platform. Okay? You can have all the flops per second you want in terms of compute, but if you're memory bandwidth bound, they mean nothing to you. Okay? So you're really looking for memory bandwidth, and that's something that the Intel Xeon Phi offers up quite nicely, and we'll see that in a moment or two. Xeon is hardware rich. It means that a lot of its hardware is dedicated to branching, branch mispredictions. A lot of its hardware is focused on very large caches, particularly last level caches. So it takes all the pain of parallelism and all the pain of low level performance engineering that you have to maybe think that little bit more about on Intel Xeon Phi away from the program. And in some sense, Xeon has been offering up a free lunch and still offers up a free lunch for quite some time. And the reason for that, a lot of the time, is due to that very large last level cache on Xeon, which we'll talk about a little bit more later on. So here's a little bit more on the die organization. So the Xeon CPU, and I'm talking about, let's say, Ivy Bridge here, because that's what's on Fume, the HPC system we'll use later on. It likes data locality, okay? Likes data locality because it's a parallel platform, but it has a large last level cache, LLC. So it has 3 levels of cache typically, L1, L2, and L3. And that L3 is big. And because that L3 is big, you don't suffer performance impact as much as you would on Intel Xeon Phi if your data is not local. Because it's a shared LL3, okay? So you see this here is your shared LL3, and you can see it's shared amongst all the cores by a ring interconnect, okay? So these LL3s they're actually, if you look at the hardware, they're actually divided up, but they're so tightly coupled that they're effectively a shared last level cache. Okay, so what that means is that you can hide latency penalties, you can hide misses to DRAM memory much more effectively, because all your threads are sharing this LL3, this last level cache, and can effectively communicate with each other by way of the LLC. Because it's large, you can fit a lot of data into it. Imagine if that LL3 was last level cache was small, which it is on the Xeon Phi, then you really need to think about localizing your data explicitly rather than leaving it to the compiler and the runtime to do it for you and the hardware. Also, something to note here is the QPI channel. Okay, so you have a PCI channel and you have a QPI channel. So Xeon processors on HPC systems typically show up as on 2 socket nodes. Okay, so you typically have 2 of these Xeon processors per node. Okay, and their 2 sockets are connected by way of a QPI interface, so quick path interface, which is proprietary hardware developed by Intel. It's a bus between the 2 sockets that allows for high bandwidth, low latency transfers between the 2 sockets. And that's something that you need to take into account when it comes to software performance engineering as well, because that reflects a NUMA node, non-uniform memory access system, which I'm sure you've talked about as part of the course already, and something that is very important when it comes to performance as well. So Xeon CPU, in terms of memory organization, we have registers, L1 cache, L2 cache, L3 cache. This is a socket here, this is a socket here. And there's your latency hits in terms of cycles for accessing each of these levels of cache and DRAM, okay? So very fast access to L1, you know all this from doing the course, probably prior to doing the course. 4-cycle latency hit for access to L1. You can typically store about 32 kilobytes of memory per core per L1 cache. L2, 10-cycle hit in terms of latency, you can fit more data into it. L3, 30-cycle hit, and you can fit more data into it again, typically 35 megabytes on high-end Xeon processors as represented by an E5 processor. Okay, so the Ivy bridges that we're going to access later on today, I think have 30 megabytes of L3 cache. And then you go out to DDR3 if you have that cache miss. And there you can see you're really paying a penalty in terms of latency. You're up to 200 cycles, so factor of 10 increase. And you've got 60 gigabytes per second per package. So there's no mention of bandwidth here, but your bandwidth to L1 is in thousands of gigabytes per second. Okay, whereas your bandwidth to DDR3 is down to 60. Okay, so you really want to avoid having to go out to DDR3 off package as much as possible. And the way you do that is by thinking about the way you cache your data. You want as much data released in cache as possible. We'll talk about that later on today. And then the exact same applies to the other socket, obviously. And then, as mentioned, you have this QPI interface between the two sockets. Hierarchical cache structure, two-way processors have NUMA architecture. Then we have the Intel Xeon Phi processors, co-processors here because it's first generation. It's a specialized platform for demanding computing applications. It's a PCIe endpoint device, comes in the form factor of a PCIe device, just like a K40 GPU or a K20 GPU, which we have on film as well, by the way. It offers up 1.2 teraflops in double precision, 2.4 teraflops per second in single precision. These are theoretical peak performance metrics here, okay? Up to 16 gigabytes GDDR5 RAM, that's only for the 7000 series. For the 5000 series that we'll be logging into later, it's 8 gigabytes of RAM, which is quite a limitation. We have 176 gigabytes per second of bandwidth to DRAM. So it's more than the two-socket device. Now, you will see in marketing material from Intel that it offers up 320 gigabytes per second bandwidth. Okay, it's theoretical. It can't be achieved on the device, and this has been a bugbear for quite a few people developing on Xeon Phi because they were expecting more bandwidth. Because with all those cores, you need more bandwidth. Okay, to feed the cores, you need the bandwidth. Okay, so it didn't offer up as much bandwidth as people anticipated, okay? So that bandwidth there is not that different, as you remember, to the two-socket Xeon platform, which was in and around 130 gigabytes per second. So that's a real issue, okay? And that's what KNL tries to improve on, okay? And we'll talk about that later on. Heterogeneous clustering. Because Xeon Phi co-processors are different to Xeon, and you have both of them in your same HPC system, you're dealing with a heterogeneous system, not a homogeneous system, okay? So you need to think about load balancing between those two different platforms because one will not, more than likely, will not run at the same speed as the other in terms of, let's say, computes per second or whatever way you want to measure your workload. And as mentioned, it runs a special Linux distro. Here's the KNC die organization. So this is the Knight's Corner coprocessor that we're talking about, okay? So have any of you seen this before? Okay, so this is new to most people. So you have your 61 cores, as we saw earlier on, okay? And they're all lashed together via this ring interconnect. So this is a bidirectional ring interconnect, okay? And it's linked together via a tag directory. So the tag directory, I'm not going to go into the details of it, but that's what maintains the cache coherency between all the level 2 caches of the cores, okay? So it's a new type of cache coherency hardware platform for the Intel Xeon Phi, okay? And it's quite effective. It's still there on the KNL, although the cache hierarchy is quite different on the KNL. Okay, so they're all linked together via this ring interconnect, and then you have several different channels out to GDDR5 as well. Okay, not enough channels as people would have liked because that we're suffering in terms of the memory bandwidth. It's only 176 gigabytes per second. Then you have a link out to the PCIe. And apart from that, I think that's pretty much it in terms of the die organization. Okay. And you'll see the die organization. What's interesting about this is how it's relative to the KNL, which we'll see in a moment or two. So here's KNC cores, and there's not too much to say on this, okay? So you have only 2 levels of cache, as I mentioned before. That's really important to recognize, okay? There's no level 3 cache on the KNC. The reason why is because maintaining cache coherency across a large level 3 cache would be very, very difficult across 61 cores, okay? So you only have two caches. And what's also important about the level 2 cache is it's not shared. It's effectively private to the core. Yeah, it's shared in some way in that they're all connected together via this ring interconnect, okay? And if you remember, I said that effectively the L3 cache on the Broadwell and on the Haswell and on the Ivy bridges is effectively connected via a ring interconnect as well, but it's much more tightly coupled, okay? So the L2 is not shared, it's private. Okay, so what that means is you need to localize your data much more so than you did on the Xeon. Okay, so you need to think about caching techniques like cache blocking, cache tiling, much more so than you did on the Xeon. You got away without doing all that on the Xeon because you had the large LLC, but you don't have it on the Xeon 5 anymore. 512 kilobytes per private L2 cache. Collectively, there's 30 megabytes of L2 cache. Yeah, L2 cache on the Xeon 5. And then you have the private L1 caches, obviously they're 32 gigabytes just as they were on the Xeon. And then here's what's most important, this large vector unit, okay, the VPU. Because the core frequency is so low, it's really there to serve legacy workloads, okay? But in order to get performance on the Xeon 5, you need to exploit this large vector unit, which we're going to call a VPU from now on, vector processing unit. 512-bit wide. Computing powers in vector units, scalar support is for legacy usage only. If you don't have vectorized code, you won't get performance on Xeon 5. Don't bother. Simple as that. Even if you can scale across 61 cores, you won't be able to beat the Xeon. So you need to scale across the cores by multi-threading, or possibly by way of MPI, and you need to vectorize your software as well.
Is there a benefit in vectorizing your code if your problem is memory bound?
Very good point. So if you're memory bandwidth bound, that's a very good point. You won't see the benefit from vectorization. So you need to solve your memory bandwidth bound problem first. I'm not saying that you should do it in that order, but without solving your memory bandwidth problem, you won't benefit from the VPU. Very good point. Yeah. So in terms of confidence levels of vectorized code amongst you guys already, how vectorized do you feel your code is? Is that something that you feel you need to spend more time on? I mean, certainly if you're leveraging dense linear algebra, it should all be well vectorized already. Anybody else? Has anybody been focusing on vectorizing their code to date? Not yet.
A little bit.
A little bit, okay. Yeah. And there are various means of doing that, and we'll talk about those later on today. Nearly ready now. KNC memory organization. You saw most of it already. You have the 2 levels of cache, L1 and L2. You have GDDR5, so slightly faster than the DDR3 on the Xeon. And then you have this PCIe bus to the host processor. Okay, so that's what we're going to call the Xeon from time to time. We'll use that interchangeably. Your host processor. So basically, the model that you use for the coprocessor is you offload data from your DDR3 into DDR5 by way of pushing it over the PCI Express bus. Okay, and you can do that now as of OpenMP4. So there are open standard means of doing that now. Okay, prior to OpenMP4, you would have had to use proprietary standards that were offered up by Intel. You know already if you use CUDA, you can use CUDA to offload over the PCI Express bus to the GPU as well. Now, because we're shaping our conversation in the context of KNL, which has just been released on the market, I'm not going to talk about offloading today, because I see offloading as effectively redundant. Okay, the KNLs that you're going to see on future systems, so if any of you are from Italy, you might be aware of Cineca, which is the HPC center over in Italy. So they're just in the process of building a massive KNL system over there. And those KNLs will be on socket, on the motherboard. They won't be in the form factor of a PCIe card. So what that means is that offloading makes no sense anymore. Okay? If you want to exploit the KNC coprocessor, if you really want to do that, and that's all you have access to, then offloading might be of benefit to you. But if you want to prepare your software for KNL, what I would strongly encourage you to do is bypass the offload model. Don't think about it, and just prepare your software for native runs on the Xeon Phi coprocessor. Okay, so you can run natively on the Xeon Phi. You don't need to offload to it. The SSH into the coprocessor, you compile on the coprocessor, or you cross-compile on the Xeon, and then you run your application natively on the Xeon Phi coprocessor. Okay, and that is a better means in my mind of preparing for KNL. Okay, but if you really think that the only system you're going to leverage over the foreseeable future is KNC coprocessor, then it might be worth considering offloading some of your key kernels, and therefore investing in the offloading model by way of OpenMP 4.0. Okay? But I'm not going to talk about it today, because there are more, in my mind, more important considerations in terms of getting performance out of the Xeon Phi processor. Getting performance in terms of offloading is not that difficult. So now we're going to talk about Xeon Phi processors, second generation. So processors being the key word here, not coprocessor. Although, remember, it comes in the flavor of a coprocessor. You want to install it in a machine, you can install it as a coprocessor as well. But the flavor that's going to be most popular is the on-socket flavor. Okay? Self-bootable. That's the thing to remember here. Okay? Socket version or coprocessor flavors. Over 3 teraflops per second of performance in double precision. 6+ teraflops per second in single precision. So quite a jump over KNC and quite a jump over Xeon. Up to 16 gigabytes of MC DRAM. MC stands for multi-channel. Okay, it's a new type of memory. It's 3D stacked memory and it's on package. So it's close to the cores. And it's something that you really need to take into account when you're running on KNL. Usually important. Okay, because it's high bandwidth memory. Okay, so you remember we quoted a bandwidth to DRAM of in and around 176 gigabytes per second for the KNC. This offers up over 400 gigabytes per second of memory bandwidth. Okay, so really targeting memory bandwidth bound kernels. Okay, so if your application or your kernel is memory bandwidth bound, what you want to do then is put your data objects into MCDRAM. Because you want to be accessing those data objects, those arrays that you're using that are part of your algorithm and that are typically memory bandwidth bound. You want to put them into fast, high bandwidth memory. And you can do that in an explicit manner, and we can talk about that later on this afternoon. Or you can do it in a transparent manner, which is a lot more easier to do, but not as effective in terms of performance. And I'll touch on those different options later on. Up to 384 gigabytes of DDR4 RAM. So you have a lot of RAM available to you on these systems. Pay the price. different SKUs will cost different amounts of money, but if you want a lot of RAM, you can get it, okay? And here's something that's quite interesting. Only 90 gigabytes per second to DDR4 in terms of bandwidth, okay? So you're going to actually pay a higher penalty on Xeon Phi KNL than you did on Xeon Phi KNC if you have to go out to DDR4. So that's why there's a big onus on trying to exploit MCDRAM as much as possible. If you have a data set that fits naturally into MCDRAM, then no worries, 16 gigabytes, it'll be enough for you, okay? But if you go beyond the 16 gigabyte limit of MCDRAM, then you need to think which data structures, which data objects should I be placing in the MCDRAM over others, okay? And that's a new way of thinking, okay? We haven't had to think that way before when x86 based platforms. Supports a common OS, okay? So it's like what I was saying to you earlier on. Don't think about Xeon Phi as an exotic platform anymore. Think about it as a more parallelized version of Xeon, okay? You can run the same OS on it as you can on Xeon, okay? So we actually have two KNL platforms coming into iCheck at the end of the month, and they come in the flavor of a workstation. So it looks like any other average workstation. Okay, there's no PCIe card here or anything like that. KNL is on the motherboard in a normal looking workstation. KNL die organization. So you can see it's quite different to what it was on KNC. We now have a mesh interconnect rather than a ring interconnect, which you would have seen on KNC. So this relaxes data locality requirements. Okay, so this ring interconnect that you saw in KNC was quite a bottleneck when it came to cache coherency over the tag directory that I mentioned to you. Even though it was a bidirectional ring, it was a performance limitation, performance bottleneck. Okay, and Intel recognized that. So what they did was they re-engineered the mesh interconnect between the cores, and now you see a 2D mesh between each of the cores. Okay. So what that does is it kind of decreases the performance penalty suffered from cache coherency across a large number of cores. But you see I've put in brackets somewhat, only somewhat, okay? There's still, I've been running on KNL for the last few weeks. My reckoning is that you still need to place just as much emphasis on data locality as you did on KNC. Okay, so it's still hugely important. And you still only have two levels of cache on KNL, L1 and L2. Now, you have different SKUs for KNL, just as you did for KNC. You have 72 cores on the high-end version of KNL versus 61 on the KNC. So more cores, not that many more. And they're divided up in terms of so-called tiles. So let's call these KNL tiles for today if we touch on them again. I don't want to start thinking about tiles in terms of cache blocking techniques, okay? And you can see there are 2 cores per tile, and it's the tile that's connected by way of the interconnect, the mesh interconnect. And within each tile, you have these 2 cores, and these 2 cores share the L2. So the L2 is no longer private to a core, it's private to a tile. And there are techniques that you can use to increase data reuse among the shared L2 tiles. Between the 2 cores, because don't forget there's still 4 hardware threads per core on KNL. So you're effectively dealing with 8 hardware threads per tile on the KNL. Now, you remember what I said to you earlier on, in that you had to use at least 2 threads per core on the KNC to get effective performance. Well, on the KNL, Intel are saying at the moment that you don't need to do that as much as you did on the KNC. Okay? So they say you should be able to get good performance with just 1 thread per core on KNL. Again, coming back to my own experience, I've seen benefit from using multiple hardware threads per core. Okay? And that comes as quite a surprise sometimes still to Intel, although this is all still very new. KNL is only a week old on the market. Okay? So, you have different SKUs. Some SKUs come with only 64 cores, for example. Now, what else? The other thing that's interesting is that you have these so-called cluster modes on KNL. And again, this is very different in terms of hardware configurations than we're used to. You have an all cluster mode, a quadrant mode, or a sub-NUMA cluster mode. These cluster modes need to be set by BIOS. Okay? So you can't set them at runtime, okay? So you need to configure them at boot up, okay? Now, as to whether some HPC centers will let you do that or not, it's still an open question, okay? So typically what you might find in HPC systems that have KNL further down the line is that some of the nodes will be configured in a certain way and some will be configured in another way. And you have to work out whether your workload is better matched to this configuration or this configuration. Now, I'm not going to go into the details of these different cluster modes, but basically what it means is the difference between a sub-NUMA mode and an all-to-all mode is that you can configure the cluster mode at boot up by way of the BIOS so that you have four quadrants, okay? So what it means is, I'm not saying this that clearly, what it means is that you can turn your KNL chip into a 4-socket chip, effectively. Okay, so just like you have 2 sockets on a node on Fun, you can make 4 sockets or even 2 sockets out of your KNL chip. So what that does is it constrains the amount of cache coherency that's required across the chip. So it also means a number of other things, but in order to exploit the sub-NUMA mode, okay, you need to have NUMA-aware software. So if your software is not NUMA-aware, you won't be able to exploit sub-NUMA mode. The default configuration for the KNL chip is quadrant mode. And we'll touch on those different modes later on in terms of software optimizations. KNL cores, we talked about this a little bit already. Even more power in the VPUs. Okay, so again, this is AVX512 instruction set that we'll be using in these VPUs. What's a little bit more unusual is that there are 2 vector processing units per core. Okay, so what that means is there's more onus on you guys to vectorize your software than anything else. Okay? So you've seen the tile configuration. There are 2 cores per tile, and they both share this L2 cache. Okay? So there is now L2 sharing but only between 2 cores. And this is binary compatible with 0. Memory organization, we've touched on this a bit already. Direct access to onboard MCD-RAM and system DDR4. Okay, use MCD-RAM as cache in flat mode or as hybrid. The default is flat mode. What flat mode means is that all of your MCD-RAM is configured in such a way that you need to explicitly program it. Okay, so what that means is that if you're in flat mode, you need to tell the compiler, the runtime, the hardware that you want this data structure, this object in MCD-RAM. Okay, so in terms of an analogy that I can think of, and it's not the greatest analogy, but if ever you've used GPUs, you've pushed data to fast shared memory on the GPU, right? So you need to explicitly program that memory. In some ways, we're talking about the same thing here. You need to decorate your buffers in such a way that they end up in MCD-RAM. Okay, so that's flat mode. Cache mode is, again, something that you configure at boot up time by way of the BIOS. What that means is that your MCD-RAM is used as an extra cache level. So it actually kind of turns into a last level cache. You can benefit from that, there's no doubt about it. Intel are quite happy so far with what they've seen in terms of some of the large-scale community codes that they've benchmarked in cache mode. So what that means is that you as a software developer don't have to worry about MCD-RAM. It's a free lunch. Okay, it's just an extra level of cache, and the compiler runtime and the hardware will work out all those nasty problems of putting data objects into the MCD-RAM for you. Okay? And the good news there is that some applications really benefit from MCD-RAM in cache mode, which is coming as a little bit of a surprise. Or you can use it in hybrid mode, so you can divvy up your MCD-RAM so that part of the MCD-RAM is in cache mode and some of it is in flat mode. I've only ever used it in flat mode, and the nice thing about using flat mode is that you tell the hardware, the runtime compiler, which objects you want in MCD RAM. So you can be more choosy about which objects go into MCD RAM and which ones don't. Because the point here is if your data structures, your data objects spill over and don't fit in MCD RAM, then you're going to suffer those performance hits from going out to DDR4. So there's real benefit in choosing which data objects and which data structures fit into MCD RAM if your data set is very large. But who knows, maybe the compiler will, and the runtime will do a good job for you, the hardware, but you can't guarantee that. It's worth trying though. The only way you can try it is if you have access to the configuration of boot. So KNL, what's new? Form factor, Haswell socket, KNC PCIe, KNL PCIe socket. What we're most interested in is socket. Core, Haswell, out of order core, KNC in order. It was a big performance bottleneck as well, the fact that it was an in order core. Now, KNL is an out of order core. Okay? It's based on Atom cores, Atom silver mode. Same type of cores you see in your mobile phone. But now Intel have a dedicated line of Xeon Phi cores as of KNL. Okay? So previously they were legacy cores, so on KNC was the Pentium 54 core that they were using. Now they have a dedicated line of cores for Xeon Phi. But the architecture is very much inspired by the Atom Silvermont architecture, which is you're effectively programming on a mobile phone core. Vectors, AVX2 on Haswell, IMSI on KNC, so that we know already that was particular to the Knight's Corner and won't be around much longer because we now have AVX 512, which is cross-compatible with Xeon as of Skylake. Memory, DDR3 on Haswell, GDDR5 on KNC, MCDRAM plus DDR4 on KNL. MCDRAM is what we're most interested in. That's the high bandwidth memory. Now, is it fast memory? That's an interesting question. What's the latency on MCDRAM like compared to DDR4? Well, the latency is excellent, but only if you're using all cores. Only if you can multi-thread across the whole system. Okay, so you'll see that the latency will stay flat against the latency of DDR4 on Broadwell, but only if you're using the full bandwidth capacity of the KNL platform. If you're not, then you'll see that the latency of MCDRAM versus DDR4 is actually worse at low core counts. Okay. RDMAs over PCIe, PCIe were integrated. So there will be integrated network chips on the KNL package soon enough, okay, and that'll be on OmniPath that you'll see on KNL. So you're talking about low latency, high bandwidth interconnect fabrics for KNL as well, okay? So you won't have to go over the PCIe bus like you did with KNC, because if you needed to communicate with a KNC process, MPI process, by way from a remote KNC MPI process, you obviously have to go through the PCIe bus to get there, and you suffer in terms of that. Whereas with KNL, you won't have to do that because the NIC will be integrated on the package. Programming, traditional programming on Haswell, native offload programming on KNC, traditional on KNL, or offload if you want that. Performance optimization, high and forgiving on Haswell. Higher means good code on KNC, 3x over KNC. So if any of you worked with KNC to date, or if any of you have been reading about KNC, you will have read that it's very difficult to get performance on KNC. That is a fact. There's no doubt about it. It's very, very difficult to get high performance on KNC. What KNL offers up is 3x performance over KNC. And it does so genuinely. But all that effort that you had to put in to KNC to get performance, you will have to put into KNL as well. Fundamentally, it's not that different. you're still dealing with a massively parallel hardware platform. Lots and lots of cores, even more cores than KNC, and the same wide vector units. So you have to contend with the same level of parallelism that you did on KNC. Okay, so things are not going to get that much easier on KNL. The only thing that's really gotten easier on KNL is the fact that it has this high bandwidth memory, the MCD. So that if you were suffering from memory bandwidth bound applications, KNL is starting to deliver on that. Using high bandwidth memory, MCD RAM. Option 1, cache hybrid mode. I mentioned these two already to you, okay? So treat it as the last level cache. Data locality techniques as usual. Okay, so cache blocking, cache tiling, all those type of techniques. Miss latency is 2x, so it's 2 times the direct DDR4 access, so that's something to bear in mind. Yeah, I think we're going to have a coffee break now. So I'll just finish this slide and then we'll go for a coffee, okay? So that's something to bear in mind, right? If you miss MCD RAM in cache mode, you're going to get such a horrible penalty from having to go out to DDR4. It's going to be a 2 times worse penalty than if you hadn't missed MCD RAM and you weren't using it in cache mode. Okay? Option 2, flat mode. This is what I've used, and this is what I think a lot of people will use. Well, it's hard to know. Okay, if you really care about performance and you're going to like get stuck in to your code and be intrusive, then flat mode is the mode for you. Application fits in 16 gigabytes of RAM. It's the first question you need to ask. Okay, is my data set small enough so that it fits in 16 gigabytes? If so, then you can use NUMA ACTL. Has anyone used NUMA CTL before? Yeah. So you can use that. So it's like a NUMA node, effectively, okay? So you can just place your data structure in MCD RAM by NUMA CTL minus M -M1 rather than -M0. And then it'll ensure that your data structure will be placed in MCD RAM. There's no guarantee that it will be, so you need to check that it is, okay? More than 16 gigabytes of data, use special allocators. Okay, so these come by way of a library called memkind. It's an open source library. You can download it from GitHub. And what that allows you to do is allocate your data structures in MCD RAM. Okay, so that's for C. If you're using Fortran, there are directives to do that. So if you're using directives to decorate your objects with Fortran, the one thing to bear in mind is that it leverages the memkind library underneath the hood. So you need to make sure that even though you're using a directives-based approach in Fortran, you're still linking to the memkind library. Some people forget that, okay? And I think I certainly need a coffee, so we'll go get a coffee. Depending on the SKU, I think the clock frequency goes as high as 1.4. Big time. Big time. No difference in case. So that's your Andel's law in effect, right? So you will suffer in that regard. And that really begs the question as to whether it really begs. It's a big issue, okay? If your application is not highly parallel, then you need to think about heterogeneous computing, okay? Because you want those sequential workloads to run on Xeon, okay? Because that's where they're good. But the heterogeneous way of computing or programming, I think, is fundamentally going to change. This is a moving target at the moment. So don't, anything I say here today is not set in stone. But I don't think you'll be programming, but you might be programming by way of an offload model, but it won't look like the offload model that you're familiar with. And I think is your application that you're interested in MPI based, I think you're better off, message passing to the KNL rather than offloading to the KNL. But I can see your problem. A lot of codes have the problem, and certainly you need to use Xeon and Xeon 5 together for those type of workloads. And mostly because of the case, because they're very large codes. It's very difficult to tackle all of the kernels in those codes, such that they're all highly parallel.
We tried something back with this process version of the KNN and with MPI reduce hashing with
No, I haven't heard anyone going on the web processor. I'm not even sure it's everyone on the market. But if you're doing that, then ask the question, why would I do it over, why am I over PCIe? Why not just do it over the RDNA in network? There's no point in doing it over co-processor, right? Because you just have that extra PCIe bus that you don't need. Because it'll have an integrated fabric, as I mentioned earlier on. So if you have an MPI code, you don't need to worry too much about offload anyway. Not even on KNC. The benefit of KNL is that you won't have to go over PCIe. You'll have an integrated fabric. But the challenge for MPI codes in terms of heterogeneous clusters, as you might know already, is load balancing. And you need to be able to effectively load balance because you're dealing with completely different methods. My note's getting very close.
slides.
Yes.